This short video will be covering the function, classification, and structure of bones. As we dive into these topics, I anticipate that for most of us that these have been covered previously as parts of other classes, and as such, I anticipate that this will be a review for many of you. Here I wanted to just remind you guys of the 5 functions of bones and of our skeletal system. I think there are nice examples throughout the body of each of these functions of bones. So a function of bone is for structure and support, provides support to soft tissues, attachments for muscles, and gives the body its basic shape. A lot of this class and maybe your other previous anatomy classes or physiology classes kind of have hopefully spoken about these and their importance and the skeletal system's importance to provide structure and support. We will dive much more into this topic as we get into specific structures that provide attachment for organs and muscles throughout the body. Another function of bone is movement. The skeletal system provides the rigid frame for which movement can revolve around. As part of this class, we will talk about movement as if someone was in space with no resistance or other things, and without the skeletal system, movement would not be provided to humans here. 3, a function of the skeletal system is protection. I think classically we think of the heart, maybe the lungs or the brain as protected by our skeletal system, which is great examples. Mineral storage. Many minerals that are important for bodily functions are stored in our skeletal system. You can see a few of them listed here. And then finally, the last function of the skeletal system is hemo or hematopoiesis, either cell production or blood production. Red marrow of certain bones produces red and white blood cells. Moving into the classifications of bones, just again, I hope as a reminder, there is 5 different classifications of bones: long bones, short bones, flat bones, irregular bones, and then the final is sesamoid bones. Moving down, the next slide gives you some nice examples. Most of the bones that we tend to think of in the body are going to be our long bones. However, we do have a fair amount of short bones, like in our wrists and in our ankles, hence the talus and the capitate here. Flat bones, sternum, scapula, the bones of our skull are all going to be flat bones. Irregular, these are going to be bones that have a lot of bony outgrowths, maybe, that provide for muscle attachment. So our vertebrae is going to be a nice example of that here. Sphenoid bone up in the skull, and as an irregular bone. And then finally, our sesamoid bones are going to be bones that are embedded within a tendon. So there's only a couple examples of a sesamoid bone. The patella is one. We have a few sesamoid bones at the base of the big toe in the flexor hallucis brevis tendon, or near our thumb. Okay, so getting into this last little bit, structure of bone. So when we talk about structure of bone, this is the classic example that I anticipate you guys have learned and talked about before. This is the structure of a long bone. I should have included that. Structure of a long bone. A short bone and a flat bone and an irregular bone and a sesamoid bone will all have different structure than this. And we'll talk just briefly about that. But I just wanted to reintroduce this, and the learning objectives have asked us to cover the structure of a long bone again. So within a long bone, we're going to have a diaphysis, and then we're going to have epiphyses, a proximal and a distal epiphysis. Generally, in between each epiphysis and the diaphysis is going to be a epiphyseal line, or the site of growth in someone that is growing. And so that would generally be there. Epiphyseal plates, they've outlined here. Okay, so inside of the diaphysis, we're going to have a primary ossification center. In each epiphysis, we're going to have a secondary ossification center. Inside of the diaphysis, we're going to have a medullary cavity, which is right here. I'll zoom in a little bit. A medullary cavity, which is going to be surrounded by bone cortex. This is that hard bone that we typically think of with the osteons and the lacunae and the osteocytes and the canaliculi. That's going to be typically found inside of this compact bone. Inside of our medullary cavity, we're going to have bone marrow, and then we're going to have that lined with our endosteum right here. And then finally, we just have an epiphysis. There's going to be two of those. The metaphysis, which is going to be the location of growth. Okay, so this is just a short review of the structure of a long bone. As we move forward, though, we realize that not all bones are going to follow this exact type of structure. We have compact cortical lamellar bone. This is going to be that bone that's found in the shaft of a long bone. But towards the end of a long bone, or in a short bone, or a flat bone, or a regular bone, we're likely to have some more trabecular or cancellous or spongy bone. That's a term that we will often hear. So spongy bone is 30 to 90% porous. It has lamellae not arranged in concentric layers there. So it's maybe a spider web might be a good analogy. It's a spider web of bone that is expanding out, and it adapts to the area of maximal stress. So we have here arranged in lines of maximum stress. Bones reshape themselves based upon Wolff's law. This is why Wolff's law gets brought up so much and so often in your physiology classes and in your anatomy classes. It's a simple law, but it's an important law to understand physiology and anatomy of the body. So inside of this spongy bone, that's found in the ends of long bones or in a short bone, for example, the spongy bone will arrange itself to provide resistance against maximal stress. So this next picture is a nice example of that rearrangement of spongy bone to provide support for areas of maximal stress. So you can see here as the force transmission lines are highlighted here as the light is shined through this bone. So you can see a very, very clear, distinct portion of bone that is thicker and darker running right through here. We've got some nice, dark, clear delineated lines coming across this way. It's generally thinner through here, but those lines pick it back up. And then we're going to have a nice area here again of clear delineated lines. These lines develop, so this is the femur bone. Hopefully you recognize that with the head of the femur up here and the greater trochanter over here, lesser trochanter right on this inside. These force transmission lines, as someone stands and runs and jumps and walks, most of the force is going to be traveling down the bone this way. And so in general, most of the force transmission lines should travel down the length of the bone. However, we also are going to need some force transmission lines this way in order to provide resistance coming from the side. You can imagine how these force transmission lines might change based upon someone's activities of daily living. Maybe if they're constantly laying on a hard surface on their side, or maybe they're playing a sport where they get hit often from the side, we might see changes in the spongy bone and the lines of force transmission as those activities change. This is a nice close-up picture of that spongy bone, how it is porous. It's not interconnected. It's going to be very different structurally from that cortical bone. And then the last slide here that I wanted to cover was that inside of each bone, there's generally a range of cortical to trabecular bone. Even inside of our short bones and our flat bones and our irregular bones, there's going to be a range of cortical to trabecular or spongy bone. So this picture here is a picture of a femur. And you can see, so the yellow and the green, the yellow into green is going to be more of our cortical bone, which resists flexion and torsion. And you'll see that most of that yellow and green is found right through the shaft of the bone and into this end. Oops, excuse me. But you can also see at the ends of this bone, here and here, we have more trabecular bone, which is more of this bluish color. And so even inside of a femur, we have a nice range, and there's some nice numbers here. The femoral neck, 75% cortical. Mainly cortical, but a fourth of it will still be trabecular. Distal radius, again, a long bone, 80% cortical bone. Mid radius, so distal radius, 80% cortical, but the mid radius, 99% cortical, which is going to be characteristic same here. But now we have some other bones, so lumbar vertebrae and irregular bone, 66% trabecular. The ultradistal forearm, 66% trabecular. I want you to notice in both of those, though, that a third of the bone is still cortical at those regions. It's a blended range. But here we have a short bone, and you think about our calcaneus, where it's located, how it has to resist forces constantly from many different directions, depending on how we walk or what we're doing. Maybe we're running, maybe we're jumping. 95% trabecular bone. However, there still is a small portion of it that is going to be cortical bone. So each of our bones exist in a spectrum. And that wraps up this video covering the structure, classification, and function of bones.